Hi, this tutorial is on alcohols and we're going to look at what happens when you oxidise alcohols, how you oxidise alcohols and the products that you make. So first of all, what is oxidation? You should already know from GCSE that oxidation can mean the addition of oxygen and reduction means removal of oxygen, or it can also mean loss of electrons, where the reduction is gain of electrons. So you should remember that method of figuring out what is oxidation and what is reduction, which is oil rig. Oxidation is loss, reduction is gain. So that's what oxidation is. Generally, in organic chemistry, the easiest way to oxidise a compound is just to burn it, because then you're reacting it with oxygen. So alkanes, alkenes, alcohols, you can react all of those with oxygen through combustion. However, we also look at milder versions of oxidation, which give you slightly more interesting products. So for oxidation of alcohols, you could burn them, but you will just get the same sort of products you would get with alkanes or alkenes. We're going to look at milder versions of oxidation where you get different organic products. So the first thing to know in this topic is that the products that you get from oxidising an alcohol depends on the alcohol that you start with. So primary, secondary and tertiary alcohols all oxidise in different ways depending on which oxidising agents you use or how you actually go about oxidising them. So first we're going to look at primary alcohols. This one's probably the most complicated because there's two different things that you can do. We'll look at secondary and then we'll look at tertiary alcohols. So a primary alcohol is an alcohol where you've got an OH group that is on a terminal carbon, so it's on the end. It's not coming off one of the middle carbons and it's not coming off like a branched chain of carbons. So this is a primary alcohol because the OH group's on the end. And to oxidise a primary alcohol or a secondary alcohol, we use an oxidising agent called acidified potassium dichromate. So this is the oxidising agent and this is the formula for it. So I've put it in different colours just to help you to remember. H plus with a slash means you've got a compound or some sort of reagent and you've got acid with it as well, so you've added some acid to it. So we put potassium dichromate and sulfuric acid together to make acidified potassium dichromate. So the H plus ion represents the acidified part of the reagent. The potassium dichromate has this formula, K2Cr2O7, and the potassium is obviously the K2, and the dichromate ion is this Cr2O7 with a 2- charge on it, obviously neutralised by the 2 pluses on the potassium ions. Now I've put this in orange to remind you that acidified potassium dichromate is orange because you need to know about the colour change that happens when you oxidise an alcohol. So you'll put a colourless alcohol and orange acidified potassium dichromate together, carry out the oxidation, and this will change colour. So throughout the course of the oxidation reaction, the dichromate ion, the Cr2O7 2- ion, which gives the compound the orange colour, gets reduced because you're oxidising the alcohol, so you reduce the oxidising agent. An oxidising agent oxidises something else, but itself it gets reduced. So the dichromate ion gets reduced down to chromium 3+ ions, and that gives you a colour change because chromium is a transition metal. It can exist in different oxidation states, so that gives the ions different colours. So when it's in the dichromate form, it's orange, and when it's in the chromium 3+ form, it's green. So you will know that the reaction is taking place because you get a colour change of orange to green. So now for the actual oxidation of the alcohol. If you take a primary alcohol and you treat it with acidified potassium dichromate, there's two products that you can get. So the first one we're going to look at is if you very mildly oxidise a primary alcohol, you will get what's called an aldehyde, which has this functional group here. In fact, I'll do it in a different colour. There you go. So this blue group, this is an aldehyde group. It looks a little bit like a carboxylic acid, but carboxylic acid would have an oxygen here. So you have to be really careful with aldehydes and carboxylic acids that you get them the right way around. So a primary alcohol is oxidised to an aldehyde using acidified potassium dichromate. And because there's two different products you can get, you need to make sure that the conditions are right if you want to make your aldehyde. So the conditions for this reaction are that it is distilled. So you carry this reaction out under distillation conditions. So that means you'll need this sort of setup. So we've got a round bottom flask with a side arm. We've got a thermometer that's going to monitor the temperature of the vapours that are going off. This arrow down here means heat, so a Bunsen burner. This is a Liebig condenser, so it's just one of the condensers that you've used in school before. We put water in at the bottom, water out at the top, and that gives it like a cold jacket to condense any vapours that come across and get them back into a liquid. We've got another little delivery tube, sidearm, and a conical flask to collect your distillate. So in the round bottom flask, you would put your primary alcohol and your acidified potassium dichromate. You would heat gently, and the reaction would take place in the round bottom flask, and any vapours of your aldehyde would go along the sidearm and would condense in the condenser and give you an aldehyde in here. Now the reason it's really important that we use distillation is because your aldehyde can further oxidise to become a carboxylic acid. So that's the other product that you could get. So we'll have a little look at that as well. Okay, so if we change these conditions, if we don't use distillation, we'll still use the acidified potassium dichromate because that's our oxidising agent, but now we want to more strongly oxidise our primary alcohol. What will happen is your alcohol will oxidise to an aldehyde, and the aldehyde will then oxidise as well. And obviously this could all take place in the same vessel. So we distill and quickly get off the aldehyde before it's further oxidised if we want the aldehyde. If we want the final product, the carboxylic acid, we change these conditions to reflux. So this is what you'd get instead. So you start with your primary alcohol, you use acidified potassium dichromate, you set it up under reflux now, so that's this setup here. So you're still using a Liebig condenser, but instead of having it going off to the side to distill off any product, you fit it up right on top of the round bottom flask. So you heat your reaction mixture in here, your primary alcohol and your acidified potassium dichromate, exactly the same reagents, but this time, instead of any vapours coming off and being collected straight away, any vapours will go up the condenser, will cool down and will fall back in. They'll evaporate, cool down, fall back in. So you're kind of blasting it and you're making sure that you react every single bit as far as it will go, and you can heat it for a prolonged period of time under reflux conditions to make sure you've got every single bit of your primary alcohol converted all the way to the carboxylic acid. But you need to remember that what's actually going on in here is it is first being oxidised to the aldehyde, and because you're not quickly removing this, then the aldehyde is also reacting with acidified potassium dichromate to give you your carboxylic acid. So distillation if you want the aldehyde, reflux if you want the carboxylic acid, and you should really be in a position to be able to draw this equipment. You need to know exactly how it's set up and how it works. So that's primary alcohols. So now if we look at secondary alcohols, compounds where you've got an OH group on one of the central carbons. So if you take the alcohol group, go to the carbon that it's attached to, a secondary alcohol will have carbon chains in two directions and a hydrogen on the other one. So this is a secondary alcohol. Secondary alcohols can only get oxidised once, so you don't need to worry about setting up distillation. You can just reflux secondary alcohols straight away, and we're still using acidified potassium dichromate. Okay, so take your secondary alcohol and your acidified potassium dichromate, put it into your round bottom flask and set it up under reflux. So there's no reason why distillation couldn't be used other than reflux will make sure that you've converted every bit of your secondary alcohol into your new product. So your new product in this case, this is called a ketone. So it looks like an aldehyde, except the carbonyl group, the C double bond O, is somewhere in the centre. It's on the carbon that the alcohol group was attached to originally. So this is called a ketone. And ketones are produced from secondary alcohols when they are oxidised under reflux conditions using acidified potassium dichromate. And ketones can't be any further oxidised, so you don't need to worry about not going too far with this one, and that's why reflux is absolutely fine at this stage. Finally, tertiary alcohols, really, really easy. Acidified potassium dichromate does not work with tertiary alcohols. So a tertiary alcohol looks like this, where if you go from the alcohol group, the OH, up to that carbon, you now have carbon chains in all three directions. So acidified potassium dichromate will not work with these, so you don't need to learn anything about oxidising tertiary alcohols, other than if you did want to oxidise it, you would just have to burn it, and then you're going to get carbon dioxide and water. So that one's nice and easy. Okay, so we know that the products you're going to make, if you're oxidising alcohols, are going to be aldehydes, ketones or carboxylic acids. So these are the products you can get. You need to make sure that you're remembering the conditions. So primary to aldehyde would be distillation, so you get the aldehyde off quickly. But if you wanted to go straight to the carboxylic acid, you can reflux from a primary alcohol or you can reflux from the aldehydes. That's essentially what's happening anyway. Get the carboxylic acid. Secondary will give you a ketone, and you would do that one under reflux conditions. So that's the products that you're going to make. Now you need to be able to test for these products: the aldehyde, the carboxylic acid, and the ketone. Now I'm going to focus on the aldehyde and the ketone because you're going to do a practical on testing for aldehydes and ketones. So what I've done is I've taken some slides from a previous tutorial, and you're going to watch through those next as to how you test for an aldehyde and a ketone. So make sure that you're making your tutorial notes on the next part as well. So the first functional groups that we're going to look at are aldehydes and ketones. So usually if you're going to test for an aldehyde, you would know that you've probably got either an aldehyde or a ketone. So perhaps you've tested for an alcohol, and you have seen that the alcohol is oxidised by acidified potassium dichromate. So we've had the orange to green colour to show that you do have either a primary or a secondary alcohol. And then you need to know, well, is your product of that oxidation an aldehyde, and therefore your alcohol was primary, or is it a ketone and your alcohol that you started with was secondary? So this is how you would test for the difference between an aldehyde and a ketone. Now, of course, it's important to remember the difference between an aldehyde and a ketone. So they're very similar. They've both got this carbonyl group, but with an aldehyde, the carbonyl group is found on a terminal carbon. It's found on the end carbon of a carbon chain. So the carbon chain would go along that way. And here you have a carbonyl group on the end. And that means that carbon's fourth bond goes to a hydrogen atom. That's the functional group of an aldehyde. A ketone is similar. It's got the carbonyl group, but the carbonyl is found in the middle somewhere of a carbon chain, maybe not directly in the middle, but it has carbon chains going off in one direction, carbon chains coming off in the other direction, and the carbonyl somewhere in between. So there are two methods I'm going to talk you through for distinguishing between aldehydes and ketones. The first one you should be familiar with is using Tollin's reagent. So you will have done this before in lesson. And to begin with, you have to make the Tollin's reagent up yourself. So you start by putting a small amount of silver nitrate into a test tube, a couple of centimetres cubed into there, and then you add a few drops of sodium hydroxide to your silver nitrate until you produce this brown precipitate. Next, you take some ammonia, dilute ammonia, and you add a few drops of ammonia until you can get that brown precipitate to dissolve. Once it's dissolved, you now have a Tollin's solution, a Tollin's reagent. So Tollin's reagent, the active part of it, is a diamine silver complex. So it's silver with 2 lots of ammonia ligands with a positive charge. And the idea behind the Tollin's reagent is that the silver in the diamine silver complex has a positive charge to begin with, but these ions become reduced to elemental silver during the process if Tollin's is able to oxidise your sample. So as we know, aldehydes can be oxidised. Aldehydes become carboxylic acids, which you've seen before with the acidified potassium dichromate. With a primary alcohol, it will oxidise to an aldehyde, and the aldehyde will further oxidise to a carboxylic acid. So we know that the positive result is going to be with the aldehyde, whereas the ketone can't be oxidised any further, so you get a negative result with the ketone. So once you have made your Tollin's reagent up, next is to add some of your sample into the test tube containing the Tollin's reagent. And then the Tollin's and the sample are heated in a water bath for a few minutes. And when you go back and have a look at your test tube, you will see that if you have an aldehyde, you get a lovely silver mirror, if you're good at it. And if you had a ketone or you had something different that can't be oxidised by Tollin's, you would have no silver mirror. Now, ideally, in terms of safety, rather than using a water bath that you've set up above a Bunsen burner, you are better using an electric water bath. This is because the aldehydes and the ketones that you're using in your sample are likely to be very flammable. So it is a bit of a health and safety concern, and you probably should be using an electric water bath rather than heating above a Bunsen burner. So just for your reference, here's a photograph of the Tollens test, when it is positive and it forms a silver mirror, and when it's negative and there is no silver mirror, so the one on the left would contain an aldehyde, the one on the right no aldehyde. So we're now going to have a little look at a second method for testing distinction between aldehydes and ketones, and this is the one that you're going to carry out in your required practical. So the second method is using something called Fehling solution, which again distinguishes between an aldehyde and a ketone. So here we've got the equipment set up to show you how you would use Fehling solution to distinguish between these two functional groups. So Fehling solution is it's a little bit strange. It comes in two solutions, so you start with Fehlings A and Fehlings B, and you have to mix those two solutions together to make your Fehling solution that will actually work on your sample. So you don't really need to know the ins and outs of it, but the Fehling solution A is just a copper sulfate solution. So it's got copper 2+ ions in it. The Fehling solution B contains sodium hydroxide, and it is the reaction of the copper 2+ with the hydroxide ions that actually gives the test its positive result. However, in the sodium hydroxide conditions, the copper 2+ would just react straight away to produce copper hydroxide. So Fehling solution B also contains a substance called potassium sodium tartrate, and its job is to complex with the copper 2+ ions and keep the copper 2+ ions in solution so that it can react with your sample, and it prevents the copper 2+ from just reacting with the hydroxide straight away. So the most important part of this is that your Fehling solution contains aqueous copper 2+ ions. These copper 2+ ions are reduced if Fehling solution is able to oxidize your sample. So obviously if it's an aldehyde, it can be oxidized, so the copper 2+ is reduced, and if it's not an aldehyde, if it's a ketone, it can't be oxidized, so the copper 2+ ions cannot be reduced. So we've got the ionic equation across the bottom showing we've got copper 2+ ions, they are reduced to copper 1+ ions. So you take your Fehling solution, which you've just made up by mixing Fehling solution A and Fehling solution B, and you add to it some of your sample, which is an aldehyde or a ketone. Again, you leave it in a water bath. An electric water bath, again, would be preferable. And after a while, you go back a few minutes and you will see that if you have an aldehyde, you would get a positive result, which is this brick red precipitate. So that is the copper oxide coming out. And in an exam, just like in an exam about Tollens, an exam question about Tollens reagent, you would say a silver mirror is formed with an aldehyde, no change with a ketone. In the Fehlings test, you would say a brick red precipitate is formed with an aldehyde, with a ketone, there is no change. So here's a photograph just to show you what they really look like. This lovely deep blue solution, that is the Fehlings that's not reacted, so it was a ketone. And on this side we've got a brick red precipitate, so it looks like a brick red liquid, but you can probably tell it's a precipitate that's suspended throughout that liquid, and that is the copper oxide, showing that the copper 2+ has been reduced down to copper, showing that the aldehyde has been oxidized to a carboxylic acid.